Okay, so in this video, I'm gonna talk about application of differential equation. So we're gonna study two growth models. The first one is called exponential growth or unrestricted growth. So for this one, it's gonna be the exponential growth or the unrestricted growth. Okay, so for this one, it's going to be the model that if you have the quantity T and at every instant, the rate of increase of the quantity is proportional to the quantity at that instant. So it's going to be, you have the differential equation given by dn dt equal to kn. Okay, so you have dn dt equal to kn. So this one turned out to be the model that like the population growth. So it's going to be population in the world growth, and you have the money in the bank with the interest compound continuously. So this one is two model that you can use the growth model, this first growth model here. And you like to find the amount of your money on the population NT. So we like to solve for NT, right? So we like to solve for NT. So from this one, you have dn dt minus kn equal to 0. And this guy turned out to be the equation that we studied earlier, which is a linear differential equation. So this one is linear. You have P equal to negative K and Q equal to 0. So you have P equal to negative K and Q equal to 0 on the other side like we had before. Okay, so it's gonna be P and Q. So you're gonna find mu by finding integrate negative k dt. Okay, so this one is with respect to time, so it's not going to be dx, and so it's going to be mu equal to e to the negative kt. Okay, so this one is going to be your mu. Okay, and after you have your mu, you're going to be able to find nt, so it's going to be 1 over mu, 1 over mu. So it's going to be mu qt, right? So it's going to be mu qt, and this guy turned out to be 0 because your q is equal to 0. So it's going to be e to the kt times 0 plus c. So it's going to be c e to the kt. And note that you have c equal to n0. Okay, so you have c equal to n0. So you have the solution of this differential equation fall into the form of nt equal to n0 e to the kt. Okay, so this one is the differential equation. Let's do one example. So you have the population in 2000 is 40 million and population in 2016 equal to 52 million. We like to find the expected population in 2030. So this one is going to be the thing that I would feel here is not going to be the population of the world. It's maybe the population of bacteria or anything that you don't have the control or anything. So it's going to be like an experiment kind of thing. So here you have N0 equal to 40 million. Okay, and you have N16 equal to 52, and you have to find N30 equal to what? Okay, so you get NT equal to N0 times e to the kt, so it's going to be 40 e to the kt. Okay, so it's going to be N0 that you use here. And then you're gonna have N16 equal to 40 e to the 6 e to the k times 16. Okay, so it's going to be this one, and N16 equal to 52. So this allows you to have 52 over 40 equal to e to the k to the 16. And this one will be 13 over 10. So it's going to be 1.3 equal to e to the k to the 16. We don't need k, we need e to the k. So I would gonna solve for e to the k. So e to the k turned out to be 1.31 over 16. Okay, so this one is e to the k, and you're gonna plug in e to the k back into the original equation. So you need e to the k. Okay, so you have e to the k equal to 1.3 e to the 16, and this one will be 40. Okay, and e to the k is the red guy, so it's going to be 1.3 and 216, and everything turned out to be your t. Okay, so you have your nt given by 40, and you have 1.3 t over 16. Okay, so this one is your nt, and you like to find n30. So n30 would be just 40, and you plug in, so it's going to be 1.330 over 16. So it's going to be 40, 1.3 to the 15 over 8. Okay, and that's all. So this one will be the population that you have. You can just use the calculator for the exact value. Okay, so you see that the thing that necessary is not going to be k, it's going to be e to the k that you're gonna plug in instead. Okay, so I just give you one example. This one is quite easy. So it's going to be just the population without any restriction. The second one is going to be the logistic growth here. The logistic growth is going to be the growth in which the growth rate of the quantity nt is jointly proportional to its current size, and it's different between its upper bound and its current size. So you see the keyword here that you're going to have some upper bound for logistic growth here. Okay, so for logistic growth, it's going to be you're going to have upper bound, and you're going to have this proportional between two quantity, which is n and the upper bound. The upper bound, we're going to use m for the upper bound. Okay, so the differential equation that we have is going to be the ndt equal to k, which is constant. Okay, so this k is constant, and you have n times m minus n. Okay, so you see that the way to solve this one, okay, so k is just constant, we don't need to care, m is just constant, so it's gonna turn out to be separable. So you see that you're gonna have n on one side and t on the other side. Okay, so you have n on one side and t on the other side, and this guy turned out to be separable. And you see that on the yellow guy can be split into fraction 1 over n subtract by 1 over n minus m times 1 over m. This one is called partial fraction decomposition, as you have seen in calculus 1. So here it's going to be the thing that we use to call in Calc 1 partial fraction decomposition, and you're gonna multiply m up. So you have m here, and you multiply m up like this, and this one is gonna be k dt. So you're gonna just integrate both sides. So you integrate 1 over n, you integrate m minus n dt, and it's gonna be log n log m minus n. Okay, so it's gonna be this one. Okay, so it's gonna be u du kind of, and it's gonna be log m over m minus n, okay, and integrate mk is going to be mkt plus c1, okay, I didn't plus c yet. So you solve for n, okay, so here it's going to be just performing algebra in order to solve for n, okay. So we're gonna solve for n, here I just say solve for the capital N. So the thing that we did here is going to be, we like to solve this equation for n, and you end up with n equal to e to the kt e to the c1m over e to the mkt e to the c1 plus 1, and you like to get rid of this term, so you basically multiply the top by e to the negative mkt e to the c1 and multiply the bottom by e to the negative mkt e to the c1. So this guy and this guy will cancel. However, e to the negative mkt e to the negative c1 still at here. Okay, let me just explain this one. So here you multiply the top and the bottom by e to the negative mkt e to the negative c1 on top mkt e to the negative c1 on the bottom, okay, and this one is given by this guy, and you're gonna let a to be, you let a to be e to the negative mkt. This one's gonna turn out to be your a, okay, and e to the c negative c1 turned out to be your c in this case. So that will be your blue color C here, and this guy will be A, okay, so it's not quite good, right? So I'm gonna use different color instead. Let's use the orange one. So this one will be your orange, okay, and this guy will be A. So it's gonna be A, okay? And so you have nt equal to m over 1 plus c a to the t. And this guy is called a logistic function. So you see that in the solution, it will involve upper bound, okay? So this one is your upper bound. Okay, and you're gonna have to find A and find C by the condition that you have. Okay, so it's gonna be when you analyze this guy. So if you curve this guy, it's gonna give you a logistic curve. So this one is gonna be exponential growth. The exponential growth gives you the graph of the exponential function, which gonna be increases without any upper bound. However, the logistic growth okay, so the logistic growth turned out to be, you see that at t go to infinity, okay, so when t go to infinity, it's gonna go to your upper bound. So you gonna see from this function that if you find limit n go to infinity, limit t go to infinity of nt, okay, so it's gonna be limit t go to infinity of m over 1 plus c a to the c, and you see that your a is e to the negative constant like this. So this guy will turn out to go to 0, and at t go to infinity, it's gonna turn out to be equal to m. Okay, so when t go to infinity. Okay, so this one will be going to go to your upper bound. The situation for the logistic growth is gonna be like exponential at first, So you see that the graph look like exponential growth at first. However, it's going to be, the growth will be decreasing. Okay, so the growth will be decreasing. So this one is concave up. This one is concave downward like this one. Okay, and you see that you're going to have the point that the growth turn out to be flipped. Okay, so the name for that point will be the infraction point. So this one, you have the point that the growth is flipped. Okay, so this one is called the infraction point. And if this one, if you recall in calculus one, is going to be the point that changing the concavity from concave up to concave down. So this one, the growth begin decrease. Okay, so the growth begin decreasing. Okay, so in this case, the growth is decreasing after this point. So you see that it's going to be growing rapidly fast, and then it's going to be decreasing after the infraction point. And the situation, for example, like in a small island, if you study a population of a rabbit in a small island, the number of the rabbit might be expected to grow very fast at first, but the growth rate would be decreasing quickly as you have like the crowding of the rabbit, and the food will be less. So it's not going to be, you're not going to be have like the growth continue forever. Like the population in the world also, like I said, sometimes if you have the lack of resources, and it's going to be kind of difficult to have the growth rate exponentially all the time. Okay, so the situation is going to be like the population of a city. Okay, so the population of a city follow logistic growth is limited to what is going to be 100,000. If the population in 2000 was 20,000, in 2016 was 50,000, what will be the population in this city in 2032? So you see the question gives you M, okay, so M equal to 10,000, not 10,000, 100,000, and it's gonna be N0 equal to 20,000, N16 again equal to 50,000, okay, and the question asks you N32, okay. So this one, you see the keyword that is going to be logistic because it's set upper bound. Okay, so it's set upper bound M, so it's going to be logistic growth with M equal to 10,000. I'm sorry, 100,000. So you get NT equal to 10,000 over 1 plus C A to the T. Okay, so this is your setup for this growth. And then you have N0. Okay, so N0 equal to 20,000. So you have 20,000 equal to 100,000 over 1 plus C. Okay, so this give you C equal to 4, right? So this one, let me also check a little bit. I don't want to miss this one. The correct C equal to 4. So after you have C equal to 4, you're gonna use another condition. So you have N16 equal to 50,000. So you have 50,000 equal to 100,000 over 1 plus 4, and you have A to the 16. Okay, so you have a to the 16 like this. So you have 4a to the 16 equal to 1. Okay, so it's going to be a to the 16 equal to 1. So you get a to the 16 equal to 1/4. So this one will be, you take the 16 root both sides. So you have a equal to 1/4, 1/16. Okay. So this one settle down our C and A. So you're gonna have A equal to 1/16. Okay, so you have A equal to 1/16, and you have C equal to 4. C equal to 4. So it's gonna be 1 plus 4, okay, time 1/4, which is 0.5, and it's going to be T/16. Okay, so this one will be your NT. Okay, so that one will be your NT. And then you're gonna compute N32 for me. So you have N32 given by 10,000 over 1 plus 4, okay, and 0.25, okay, and 32 over 16. So you see that I did put 32 into the function, okay, so I just plug in t equals to 32. And this one will turn out to be nice number. So you have 100,000 over 1 plus, so it's gonna be 1/4 square. So this one will be 1/4 square. So it's gonna be what? It's gonna be 1 plus 1/4. Okay, so 4 will cancel with 1/4 square. So this one will be given by 10, not 10, 100,000 over 5/4. So it's gonna be 80,000. Okay, so you have N32 equal to 80,000. So you see that the time is double. However, you have the population like grow slowly. It's not going to be double. Okay, so you see that is going to be going very fast. So 16 years, the growth turned out to be 50,000. Okay, and you should expect that it should be more population because this one is 50,000. Okay, so you should expect that it's going to be more than 80,000. However, you have the limit for 100,000 here, so it's going to give you the growth equal to only 80,000 people in 2032. Okay. Finally, the next one, you have a leg is stocked with 100 feet. 3 months, okay, so there are 250. And lack or the ecology of the lake predict that the lake can support 1,000 fish. So here is gonna be your M. Okay, so you have your M equal to 10,000, 1,000, and here you have N0 equal to what is called 100 fish, and 3 months, so you get N3. Okay, find the formula. Okay, NT after it had been stocked, so you like to find NT. So here you use N0 equal to 100, N3 equal to 250, and you have M equal to 1,000. So you have logistic growth NT equal to 1000 over 1 plus C A to the T. And you're gonna proceed to find C and A from these two conditions. So you have this guy and you have this guy. So you're gonna use them to find C and A. Okay, I leave you with these two numbers, and at the recitation, we're gonna finish this one with C and with A together. Okay, so that's all for the differential equation. Okay, I hope that it's not gonna be difficult. It's gonna be just two types of differential equation that you have to concern. It's gonna be only the separation, the separable equation and linear equation, and the application you have two formula. It's gonna be exponential growth and the logistic growth. Okay, so that's all. Okay, so see you next week.